acid-base titration. This is what we're doing in lab today. This is a technique, and it's a technique that involves stoichiometry. The idea here is that we're going to have a chemical reaction occur between two solutions. One solution we know the concentration of, the other solution we don't have the concentration of, and that's what we're trying to find, is the concentration of one of the solutions. We're going to react the solutions in stoichiometric amounts, and then we can use stoichiometry and calculate the amount of the concentration of the unknown solution. So we have a substance of known concentration reacting with another one. This is commonly done with acids and bases, but it can be done with other chemical reactions as well. The net ionic equation for a reaction between an acid and a base is that you have a hydrogen ion from the acid reacting with a hydroxide ion from the base, producing water. It doesn't matter what the acid is, hydrochloric acid, nitric acid. An acid dissociates into hydrogen ions and something else when you put it into water. The bases that we're dealing with in this class are all metal hydroxides. The sodium ion ends up being just a spectator ion. So here we have an illustration, and we're just showing the hydrogen ions. So here in this Erlenmeyer flask, we have a solution of an acid, and it's got a certain amount of hydrogen ions in it. And what we're trying to figure out is how many moles of hydrogen ions are in that solution. So we're going to put a sodium hydroxide solution whose concentration we know into a burette, which is just a fancy piece of glassware that's convenient for measuring and dispensing amounts of liquid. So we're going to add sodium hydroxide. As these hydroxide ions come to this acidic solution, the hydroxide ion and the hydrogen ion react to form a water molecule. And we're going to keep adding the sodium hydroxide until we've reacted all the hydrogen ions. Now the trick, of course, is how do you know when you've reacted all the hydrogen ions? And we're going to use what's called an indicator for that. What will happen in the titration we're doing today is the solution will turn pink. That's called the equivalence point. That's where we've added an equal number of moles of hydroxide to the number of moles of hydrogen ion that are in the solution. The equivalence point is usually signaled by an indicator. The one we're using today has a long, hard-to-pronounce name, phenolphthalein. It's even harder to spell. These are usually dyes whose color depends on the acidity of the solution. So this is a substance that if you put it into an acidic solution, it's colorless. But if you have it in a basic solution, it's going to turn pink. And so that alerts us to the end of this reaction. This is actual pictures of what's going on. Here we have a clear solution. This is hydrochloric acid, and it's got a couple drops of phenolphthalein in it. We've got sodium hydroxide solution in the burette. As we add drops of sodium hydroxide, we'll see a little bit of pink forming, but if we swirl this around, the sodium hydroxide reacts with the hydrogen ions and the pink disappears. When we get to the end point, or the equivalence point, one drop of sodium hydroxide will cause the whole solution to turn pink. And then we know that we need to stop. So this is the sort of calculation, and we talked about this in the end of chapter 13. It's solution stoichiometry is all that it is. So we have the titration of a 20 ml sample of sulfuric acid solution of unknown concentration, and that needs 22.87 milliliters of 0.158 molar potassium hydroxide. What's the concentration? Well, the equation wasn't given here, but we can write that out. Sulfuric acid, H2SO4, is going to react with sodium hydroxide. And it's going to form, what it's going to do is it's going to do that ion swapping thing we talked about in a previous chapter. You're going to get sodium sulfate and water. And in order to balance this, we're going to need 2 of the sodium hydroxide molecules for each sulfuric acid molecule, and we're going to end up with 2 water molecules. The equation has to be balanced for this to work. In the lab you're doing today, the equations were given to you. 20 milliliters of the sulfuric acid, so that's 20 milliliters of this. And it required 22.87 milliliters of the sodium hydroxide. And that concentration was known. It was 0.158 moles per liter. What we want to know here is the molarity, the concentration. So instead of finding the volume of a known concentration, we're finding the concentration of a known volume. We know the volume. What we need to find then is the moles of sulfuric acid. So what we're going to do is we're going to go liters to moles to moles. We're going to end up with moles of sulfuric acid. And then the molarity equals the moles of sulfuric acid divided by the liters of sulfuric acid. They gave us milliliters, but we can convert that into liters. So we're going to start with the volume of the sodium hydroxide, and we're going to use the concentration, the molarity, as a conversion factor to get the moles of sodium hydroxide. We use the mole ratio from the balanced chemical equation to find the moles of sulfuric acid. Then we stop and we go over to this molarity equation and we take the moles we just calculated and divide by the volume. So we've got 2287 milliliters. We need to convert that to liters. And then we're going to use the molarity, moles, no, not the molarity, the molarity. Sorry, moles of sodium hydroxide per liter of sodium hydroxide. So the liters cancel out. And then we've got moles of sulfuric acid to moles of sodium hydroxide. This little extra step here is just because we measure things in milliliters instead of liters. So milli means 10 to the minus 3. So 10 to the minus 3 comes up here. The concentration was given. It's 0.158. 0.158. Mole ratio comes from the balanced chemical equation. 1 mole of sulfuric acid to 2 moles of sodium hydroxide. 1 to 2. .87 times 1 times 10 to the minus third times 0.158 divided by 2. 0.001807. The 3 sig figs I'm carrying 1 extra one along. And that's moles of sulfuric acid. So that's the numerator of our concentration. And what's the volume of the sulfuric acid solution? 20 milliliters. So we figured out the number of moles of sulfuric acid, and now we have the volume. We have to convert that volume to liters. .0200 liters. So we stick that in here, 0.0200 0.200 liters. We come up with 0.0903 moles per liter. Any questions? This is the conversion factor between milliliters and liters. I'm just converting from milliliters to liters. There's different ways to do this. I'm trying to pick the most straightforward way. It's not the shortest, but it requires the least understanding. Any other questions?
So the one behind you.
This is my own scribbling on the board.
I'm